Dear friends, today we are going to see an introduction to the basics of vectors. In physics, we are studying natural phenomena where we try to establish relationship between quantities. Quantities dominate our scenario. See, for example, a quantity, say mass, is specified with a number along with a unit, say 15 kilograms. Likewise, density is mass per unit volume, mass by volume. Say kilogram per meter cubed is the unit. So 1500 kilogram per meter cube is the density of some substance. That means this number and this unit both are important in specifying that physical quantity. But there are certain physical quantities in which, in addition to this number representing the magnitude and the unit, we need to specify its direction. Such quantities are called vectors. Vectors require both magnitude and direction. Examples of vectors: displacement, velocity, acceleration, force, momentum. All these are vector quantities. Those quantities whose specification do not require a direction are called scalars. Mass, density, temperature are examples of scalar quantities. Consider an object resting on top of a smooth table. Attached to this wooden block is a string which passes over a pulley, and the string has at its other end a weight suspended. Suppose you increase or decrease the height of this pulley at one position, this wooden block starts moving to the right. We find that the pull on this wooden block remains the same. The force, magnitude of the force is the same. But what happens as we reduce the height is this direction changes. And its effect on this block depends not only on the magnitude but on the direction. So for vector quantities, both magnitude and direction are equally important. So for vectors we have in general magnitude, direction, units. Now let us consider the displacement vector. You consider a two-dimensional plane in which a point P1 is specified by the two coordinates x1 and x2. Another point P2 is specified by the coordinates x2, y2. This line joining P1 and P2 represents the vector displacement from P1 to P2. It represents the displacement of the object from P1 to P2. Its magnitude is given by the length of this line, and the arrow and its orientation space shows its direction. Now let us see a convenient way of representing this displacement. First of all, we will see how points in space can be represented with the help of what are called position vectors. Position vectors. P1 is represented by a directed line starting from the origin. Say R1 is the position vector of P1. R2 is the position vector of P2. What about the displacement vector R12? That is a vector directed from P1 to P2. That is a displacement vector is given as R2 minus R1. R2 minus R1 is the displacement vector, or R2 is equal to R1 plus R12. This vector R1 or R2 can be specified with the help of what are known as unit vectors. In Cartesian coordinate system, we can specify 3 unit vectors along the mutually orthogonal axis x, y and z, the I, j, k. The I vector is parallel to the x-axis, j vector parallel to the y-axis and k vector parallel to the z-axis. If x-axis is chosen like this, y-axis like this, and z-axis is outwards, then that coordinate system is known as the right-handed coordinate system. That is preferably used in physics. That is the convention followed in physics. In right-handed coordinate system, the ijk unit vectors will help us specify the position vectors. How that helps us, we will see. Ijk are unit vectors. Unit vectors means their magnitude is unity. They have no units, no dimensions. Their magnitude is unity. Their directions are fixed. I vector is parallel to the x-axis, j vector is parallel to the y-axis, and k vector is parallel to the z-axis. In this two-dimensional case that we are discussing, you can see that the coordinates of these points are x1, y1. The coordinates of these points are x1 and y1. Then what about this vector? This vector has got a magnitude x1 and its direction is taken care of by the unit vector I. What about this vector? This vector has a magnitude y1. What about its direction? It is parallel to j, unit vector j. Therefore y1j. Thus we can specify R1 vector as x1i plus y1j. What about the magnitude of this vector R1? That is the length of this segment. That is modulus R1, or the length of this vector R1, which is simply written as R1 without the arrow on top, is the hypotenuse square. This R1 square. Therefore, the magnitude is given by square root of x1 square plus y1 square. Thus, we can represent a vector with the help of unit vectors I and j. R1 is x1i plus y1j. Similarly, R2 is x2i plus y2j. Therefore, the displacement vector R12 is R2 minus R1 is equal to x2 minus x1 I plus y2 minus y1 j. This represents the displacement vector in terms of ij unit vectors, x2 minus x1 I plus y2 minus y1 j. That represents the displacement vector. What about the magnitude of this displacement vector? R12, simply R12 is equal to square root of x2 minus x1 square plus y2 minus y1 square. Ijk, I told you, are unit vectors. Their magnitude is unity. Their directions are fixed for Cartesian coordinate systems. They have no dimensions or units. When we express a displacement vector in terms of the ij displacement vector, in terms of ijk vectors, the coefficients x2 minus x1 having the dimensions of length, y2 minus y1 having the dimensions of length. The I and j do not have any dimensions. Now let us consider general vectors. A vector A is equal to AXI plus AYJ plus AZK. Its magnitude is given by modulus A is equal to square root of AX square plus AY square plus AZ square. For position vector, we have seen the representation is xi plus yj plus zk. Likewise, we can represent any vector in this form with a ijk, ax, ay, az. They are known as components. X component of the vector, y component of the vector, and z component of the vector. For position vector, x, y, z are the x coordinate, y coordinate, and z coordinate of the point whose position is fixed by the position vector r. Now, what about the magnitude of this vector? Magnitude of this vector r is equal to square root of x square plus y square plus z square. You can divide vector r by its vector r divided by the magnitude of the vector. What we will get is x by r I plus y by r j plus z by r k. These x by r, y by r and z by r are known as the direction cosines of the vector. Now this vector r can be written as equal to this. What is this? Vector r divided by the magnitude of that vector is a vector parallel to this r but having unit magnitude. That is vector, this is a unit vector in the direction of r. So vector r can be represented as magnitude of vector r times a unit vector r in the direction of vector r. From this, vector r is equal to magnitude of vector r times a unit vector r. When we write it in this form, we find that it separates out the magnitude of the vector and the direction of the vector. This unit vector takes care of the direction of this vector r, and the r here, this one, takes care of its magnitude. This is the unit vector. Unit vector involves the direction cosines and the ijk triad of vectors. In a similar way, we can write down for the general vector a unit vector can be introduced. That is, vector A can be represented as magnitude of vector times a unit vector in the direction of A. Now let us consider vector addition. Vector addition, if two vectors are acting on a body, for example, two forces are acting on a body, these two forces can be replaced by a single force which produces the same effect. That force is called the resultant of the two forces. For vectors, general vectors, it is the resultant of the vectors. Say A and B are two vectors acting at a point. A plus B is equal to B plus A. For vectors, they need to satisfy this equation. A plus B is equal to B plus A. That is, vector addition is commutative. Also, A plus B plus C, three vectors, A plus B plus C is equal to A plus B plus C. That is, vector addition is associative. This shows vector addition is commutative. The order is not important. Only quantities having both magnitude and direction which satisfy these requirements can alone be described as vectors. Now let us consider two vectors acting at a point. How to find the resultant of these two vectors? Say A and B are two vectors. A vector is represented by a directed line segment. Its length will be proportional to the length of this line, and the arrow shows its direction. These two vectors are acting at this point. What about its resultant? The resultant can be found by drawing a parallelogram like this. And the diagonal of the parallelogram will represent the magnitude and direction, the resultant of these vectors. Let the angle between the two vectors A and B be theta. Let the resultant make an angle alpha with vector B. Now let us find what is the magnitude of the vector R if magnitude of vector A and magnitude of vector B are known. Magnitude of vector A is denoted as A. Magnitude of vector B is denoted as B. Magnitude of vector R is equal to R. Let the vectors be acting at this point O and Q. Let this point be P1 and you drop a perpendicular from Q to the line extended, that is P2. In this right angle triangle, being A being here, opposite side also will be A. What about if this is B, this is also B? What about the resultant R? R is equal to A, B plus A. Also, this is A plus B. Vector R can be written either as B plus A, triangle of addition, or A plus B. Now we are going to find the magnitude of R. Magnitude of R is this length. This length square is equal to the sum of the squares of these two sides. That is by the Pythagoras theorem. That is, R is equal to square root of B plus, B is this length, plus this length is A cos theta. Cos theta, because this angle is theta, we have two parallel lines, and if this angle is theta, this also will be theta. B plus A cos theta square plus A sin theta square. Expanding inside this square root sign, we get B square plus A square cos square theta plus 2ab cos theta plus a square sin square theta, or R is equal to magnitude of the resultant is given by square root of a square plus a square cos square theta plus a square sin square theta is a square multiplied by sin square theta plus cos square theta, that is 1. A square plus b square plus 2ab cos theta. Now let us see what is the direction of this resultant of two vectors. Resultant is given by this alpha, how it is oriented with regard to vector b. Tan alpha is equal to opposite side by adjacent side. Opposite side is a sin theta divided by b plus a cos theta. Or alpha is equal to tan inverse a sin theta divided by b plus a cos theta. This gives the direction, how the resultant is oriented with respect to vector b, and this gives the magnitude of the resultant. Thus, if two vectors are given a and b, and what the angle between them is also known, if it is theta, then we can find the resultant's magnitude and direction in terms of these three things. Say the magnitude of vector A, magnitude of vector B, the angle between the two vectors. Thank you.